assuming this works. Okay. So depending on what the test is, I will give you the review and we'll go over the class before. So if the test is next Wednesday, you'll get the review either later today or tomorrow. And we'll have nothing new on Monday, so I'll probably go through Zoom instead because that's easier to interact. And then test on Wednesday. And if the test is Thursday, Wednesday will be the review and so on. So go on that. So otherwise, today we're going to continue in through chapter 4. But before we do, let's go back and do at least one example from 3.11. So they say find the surface area of the sphere below the line z equals 1. They then add together with the disk that would close it. So with the disk. But that's kind of silly. Because that we don't need an integral for. So I'll just do that now and then we'll do the part that really matters. So at z equals 1, of course, we get the circle x squared plus y squared is equal to 3. So what is the area of that disk? And it's just a circle, so therefore the area is pi r squared. Since the circle is x squared plus y squared is equal to 3, r squared is 3. So that's the disk. Now what we want is the part of the sphere, and here's what it would look like from the front. So we have the part of the sphere that is below z equals 1. Okay. So what we want to do is kind of go through the full thing, which is we know that the surface area, if we have it in parameterized form, we can do it fairly easily. Here it's a bit more complicated because we'd have to get c in terms of x and y and take the partial derivatives. We don't really want to do that because it's going to be a messy one. So we want to do parameterization. And for that, we will use the spherical parameterization. But we know here, we know what rho is. Rho here is what? So rho here is 2. Oops. So there's our parameterization. Then we have our parameterization altogether is, in terms of theta and phi, is these x, y's, and z. So obviously I don't have to do the room here, So let me look at the next slide. So first, any questions about this setup? So we're just using the usual spherical coordinates. So first, let me remind you that this is the general thing if we have a parameterization. Here it's in terms of u and b, what I've just written, but we have really theta and phi. So what we need is the derivative of r with respect to phi. So x is equal to the 2 sine of phi cosine of theta. So therefore its derivative with respect to phi is just becomes the cosine phi. Same type of thing for y. And same type of thing for z. So as the derivative, and as always, you're going to correct me. This is the derivative with respect to phi. And the derivative with respect to theta is now for x, the sine of phi stays the same, and derivative of cosine is the negative sign. And nicely, the derivative of z is 0 with respect to theta. And then we want the cross product. It's not going to fit nicely here, so I'm just going to put that's what we're getting. So put the first vector in the first row, second vector in the second row. As usual, it's not really going to matter which one you do first. And so we get for the I, we're going to get using the second and third column, we're going to get negative, negative, so 4. For the J, we're using the first and the third. So there we'll again get negative, negative, because the two negatives for the negative 2 sine phi and negative 2 sine phi sine theta will cancel. Forget that. And then the next one, we get the lovely thing. We get 4 sine phi cosine squared, and then minus minus, so plus 4 sine phi cosine phi sine squared. So we're going to get this. So I can fit them. I'll put them together. So first, let me stop here. And just give you a chance to check to see if I messed something up. I should say as I'm waiting. As usual, if sound goes out, let me know and I'll try putting it back in and so on. The first little thing, and then you'll tell me if I have other problems, which is this. Obviously, I can simplify cosine squared plus sine squared is 1, as someone said. So that part at least is simple. And now here we want now the magnitude. And it actually turns out this isn't too terrible, but let me call this A, B, and C. And then you'll tell me what the limits are. And the magnitude is the square root of the sum of the squares. So here we're going to get, I said I'm going to be lazy. Actually, I need one more thing, so luckily I still have some space. And it doesn't really matter which order. So let's say d theta. One of those is easy. So if you go back to the picture on the previous one, we're doing the full sphere except below z equals 1. So what is the range for theta? Right, so 0 to 2 pi. So that one's easy. But let me draw the picture up here again, which is we have from the front. We have that. And since I'm measuring this, I need to know what that is. So to get the other limit, the inner limits, we need to look at z equals 1. So z we know is the rho cosine phi, except we know rho is 2, so it's 2. So this one can actually do. What do we get for phi? One is cosine 1/2. Should be one of the basic ones. Is that next to the cosine rho? Oh, yes. I wasn't sure where you're looking. So yes, that's here is 2 cosine phi is equal to 1. So pi over 3. And now is that going to be the upper or lower limit for our integral? Yep, because we're measuring from the positive z-axis. And otherwise, we go all the way down. So what's the upper limit? Yep. Remember, unlike theta, pi takes us all the way around the sphere. So there's the setup. In some ways, as I said, it's actually better than it looks, because if you look, you can kind of see that we're going to start getting sine squareds and cosine squareds of theta. So we're going to start getting more canceling like we did here. So it actually does simplify quite a bit. So I actually get that it simplifies to 4 sine of phi. So the reason that the top limit is pi is, remember, what we're doing is when we're looking here, remember the phi is measuring from the positive z-axis. So we're measuring down this way. So we hit the sphere at first at z equals 1. So that's why the bottom limit is pi over 3. And remember, we're kind of going down from both sides, 12 sides at once. Therefore, when we hit pi, we hit the negative z-axis from both sides at the same time. So it sweeps down and hits both of them by, if I go just to pi. So going from 0 to pi would give the full sphere. 0 to 2 pi will then sweep it around to get the full sphere. So the full sphere is always theta from 0 to 2 pi, phi from 0 to pi. And yes, again, phi is measured from the positive z-axis, so we're measuring down from this positive z-axis. So in some ways, this last bit here, don't worry about too much, because as usual, I probably just have you set it up. So this is kind of a tedious one, but all the steps are there, which is what we have to do is we get the parameterization, which I might give you. You're only expected to know a few parameterizations. You take the two partial derivatives, because there should only be 2 dimensions, because we're looking at a surface, which is 2 dimensions in 3 dimensions in free space. Take the cross product, and then look at the integral of the magnitude. So here's one more all the way through. So any questions on this? So I'll ask again tomorrow, see if you want to do any more of these. I think 20 and 20 are also sort of complicated ones. You won't get something that complicated in the test, but okay. Can you hear me now? My internet, this other internet died out, so sorry about that. So any questions on this before I erase? Okay. So 4.1, remember, was just a bunch of definitions. So you can try the homework, but I'll skip those for now. So again, tomorrow you'll let me know if you have any questions on it. And the reason I'm skipping it for now is we'll actually use it in some of the later sections. So I'll do examples when we get to the later sections. So I might as well wait until then. And this way we can actually get to real applications. So as I said a couple classes ago, in some ways chapter 4 is 2 types of integrals. One is this section, line integrals, and the other is flows or flux integrals. And for both of them, basically we do the basic definition and then do a couple other ways you can do it, either simpler or just another way. So there are 3 sections dealing with line integrals and then 3 sections dealing with flows. So 4.2 is the introduction, the basic definition of line integrals, and the next 2 sections will be doing cases where it's a little bit easier. So here, this is a line integral. And let me make a specific one, because then you can kind of see why it's defined this way. Which is if the f here, the function, is a force, and r is a curve in 3 space, then this integral is going to give us the work. So you can kind of see why it's defined this way, because we know from chapter 1 that work is equal to the dot products of force and the distance traveled. And here it's kind of the integral thing, which is, well, we can't assume that here because we're not going in a straight line. So we're going to break up the path into lots of little pieces, get the work on each of the little pieces and add them up. But you can see why it is defined as a dot product. So let me make it more specific. Oh, sorry. Can you hear me now? Hello? Yes, okay. Sorry about that. So if F is a vector field and R, that's supposed to be R, is a piecewise regular parameterization of a curve C, I have two parentheses there, is more specifically this thing. So this is an R. So it is, what is the vector field at the point at time t, which we get by plugging it into R. And this is supposed to be a dot product there. Times R prime. And I'll say more specifically once we do an example, because then it's easier to say what each piece is doing. But R prime is moving along a straight line for a very short distance. So as I said, sort of what we had at the beginning. So we integrate with respect to t, right? So as I said, it'll be easier. Let's do an example, and then it's easier to see what everything is. But so any questions on this? This is sort of in the background. You'll see when we actually do it. So given a vector field, so this is, as I said, could be gravity, could be flow, could be whatever you want. This particular one, I'm pretending it is the gravity, that way we get work, or force to get work. So moving along this curve, subject to a force, I want to find the work to move along that curve. So to do directly the definition I just did, what we have to do is parameterize. And as I said a few classes ago, really basic parameterization is always easy. So just let x, one of the variables, be t, and let the other variable be the function in terms of that. So there is our parameterization of y equals x squared. And according to the theorem, what we need is what is the function if I put in the parameterization, x equals t and y equals t squared, which is, this is saying what is the force at the point t. So we get 6 times t squared. So 6x squared times y. And then x
Shouldn't that be x cubed?
plus 2y. Oh, so I've messed something up here, which is as usual, and this time no one has caught it yet, which is at x equals 2, what is y according to my curve? 4. So I have to change one of two things. Either I can change the 8 there to a 4 to make this work, or I would let y equals x cubed. So I think I'm going to change that to a 4, because otherwise this doesn't work. So I get that. Same type of thing. I need the derivative of parameterization. Which is just the derivative of that. That's pretty easy. And then t is the same as x, basically. So t goes from 0 to 2. And we have that. So the dot product of those two. Now here, let me say kind of what both pieces are, which is this is the force at a particular place, in this case at t. And this is the vector of the tangent line. And it says how much does x and how much does y change if we change by delta t. So this is basically we're moving along the tangent line for a very short distance, particular for an infinitesimal, because we're going to let the distance go to 0. And so you can see it really is the chapter 1 question, which is we have force and distance. And so we take the dot product of the force and the distance to get the work. And then we add them all up. So when I take the dot product, I get that. I do the usual thing, I take the antiderivative. I messed that up. T, that's a cube, so this should be, let's see, 3. I get some number. In my notes, I had it x cubed, so I'm getting a different number, but you're getting whatever 6 times 32 over 5 plus 16 over 3 plus 16 is, so whatever the number is. And that would, in this case, be the work. Here I don't start with units, so you can't tell me what the units are, but you could. So joules or foot-pound type thing like we did in chapter 1. So here's basic one, which is you're given a vector function, you're given a path with a parameterization, and we want to find this line integral, which in this case is work, but in other cases could mean something different. A couple things. One is there are in some ways lots and lots of different possible parameterizations. So I could be weird and I could have made x equals t squared. And then in that case, y would have been t to the fourth. Or I can make x be equal to negative t and y equals t squared. So there are lots of possible parameterizations. Whichever parameterization I use, I'm going to get the same number. So it doesn't matter which one you use. On the other hand, I'm going from 0, 2 to 2, 4. If I use a different curve, then of course I might get something different. So here I went along y equals x squared. I could also go along the path y equals 2x. And if I use the path y equals 2x, I might get a different number. And that'll be something that'll come up in the next section, I think. Because there will be certain cases where the path does not matter. But in general, it might. So any questions on this? So let me do this a second way to show that if we want, just like the last 3.11, kind of two ways of doing it. I like this one better, but whichever. Which is, so let's go back to this. Let me write down the problem again. So we have this. So if I call f p comma q, you can also write it like this. So you can see, again, it's sort of a dot product. And you have to notice here is y is equal to x squared. So we kind of do a substitution type thing. Therefore, dy is equal to 2x. Therefore, in this particular case, we get integral from 0 to 2. 6x squared, oops, to the usual substitution. So y is equal to x squared dx. And then x plus y. And then dy. And you can see it's basically like a dot product of the function with the derivative. So it really is the same type of thing. But if you'd rather. This only works if we're using kind of this comes from the really basic parameterization where we let x be x and y be f of x. So if the function doesn't work nicely with that type of parameterization, probably won't work nicely with this either. So any questions on this variation? So let me add on. So if I have a path that has a couple pieces, C1 and C2, and as you might expect, you can break it up into two pieces. Or if they're three pieces, you can break it up into three pieces and so on. So you can break it up into the multiple pieces. And in a similar way, one thing is here when we talk about path, we're talking about a particular direction. And this one should be obvious if you think of it as work. So if I have a path and I go in the opposite direction, how does that compare to if I go in the original direction? So I'll write this. What's the relationship between the two? The first one is equal to what in terms of the second one? Yeah, it's negative, right? Because if I do positive work going in one direction and then the opposite direction, I'll be doing negative work. So let's stay with the example we just did. Is still equal to the 6x squared y, x plus 2y. But let me add pieces. So I start at the origin. I move up to 2, 4. So I actually should have gotten that number along the curve y equals x squared. Then I go from 2, 4 along the line to 0, 2. And then I go from 0, 2 along the axis to 0, 0. So let's call this C1, C2, and C3. So in some ways, just more practice. And the one parameterization I assume you should be able to just read off is lines. So we want to get the parameterization from there, from 2, 4 to 0, 2. And there are usually a couple different ways of doing it. So one way you could do it is just like we did in chapter 1, which is I have 2 points. I can get the equation of line by doing this. So in this case, AB would be the change in x and the change in y. And it doesn't really matter which way you go. Or I can just read it off. So x goes from 0 to 2, so I can do x is equal to 2t, y is equal to 4 minus 2t. Wait a second. Well, I'm not doing well. So I should have just used the original one. I could do something like that. So let me go back and start this again. Sorry about that. Because I don't have room anyway. So if I'm going from 2, 4 to 0, 2, I subtract the first from the second. So I do 0 minus 2. 2 minus 4. Where I start. Plus the vector. And the nice thing about this is, in this case, t will always go from 0 to 1. So if you use this type of picture, this type of parameterization for the line, you don't have to worry about what the values of t's are. So here we would get that our parameterization at t is equal to 2 minus 2t and 4 minus 2t. This is for C2. And we know that from the previous one that there are the two steps. We now have to put this parameterization into the function. So we have these 6x squared y, and then x plus 2y. And the derivative is that. So it's a bit messy, but it works out. This I'm definitely not going to do. But any questions on the setup? Okay, so I'll only do C3. And to show that sometimes it'll be nicer, so this one I might actually do. So here it's the line from 0, 2 to 0, 0. So one of them is easy. So here's a parameterization. Well, x is obviously 0, because it's 0 on the full path. And just to be different, I'm going to let y equals t. I could do exactly what I did in the last one, which is we're going from 0 to 2 to 0, 0. So I could again find the vector from 0, 2 to 0, 0, plug it into the line equation. But as I said, just to be different, this will make it so the numbers are slightly nicer. But we do have to be careful. Because here, we start at t equals 0, and we go to t equals 2, and we go to t equals 0. So when we do the integral, kind of a weird one. We go from 2 to 0. We could flip it and then put a negative in front. That would be the same thing, but whichever. So again, we have lots of possible parameterizations. And again, plug in. So 6 x squared y, x plus 2y. I'm sorry, I'm going to put in the derivative. Dotted with 0 to 1. And so the dot product is just 2t. The antiderivative is t squared from 0 to 2, which is negative 4. Because again, this can be negative. You can do negative work. So here's a couple more. Any questions on this? And I should say, once we get each of them, so we have the 3 pieces, we would add them all together and get one number. And since some of these are positive values, so for example, in C1, if you look at the function, as x and y are getting bigger, the force is getting bigger. So as we're moving along C1, we're going to be doing positive work. On the other hand, on C2 and C3, we'll probably be doing negative work. So it is possible, if I go all the way around, I end up doing no cumulative work. So 0 is a possible answer. This means I've added up and everything cancels. Okay, so any questions on this? Obviously, we have to do more examples. Okay, so let me erase. So one more example. So here's our path. We're moving along the circle of radius 2. And we're moving along the curve. And I want to find, again, pretending that this is a force, find the work to move from the 2, 0 to the 0, 2. So the first thing we need to do is get a parameterization. In theory, we know it's x squared plus squared is equal to 4. So we could do that. But since this is a circle, what type of coordinates do we probably want to use? Polar. So therefore, we're going to do our parameterization is x is equal to r cosine theta. But r, of course, is 2. And this time, so I don't forget to write it down, let me take the derivative. So then we take the derivative. Two there. So there's our parameterization of our path. You'll give me the limits in a second. So we put our parameterization into our function. So y, which is 2 sine theta, comma x. There's our function. Now take the dot product of our derivative. path. See, it's the quarter circle, so therefore 0 to pi over 2. And here, I made it annoying because we get that. You probably did sine squared, cosine squared in Calc 2, but I'm not going to make you do it again. You have to do the half angle formula to get sine theta in terms of cosine of the theta over 2, but we're not going to do that. So this, I'll just put dot dot. As usual, you would mostly set these up anyway. So that'll be our integral. So it's on this. So for tomorrow, you're going to do two things. One is you're going to go to the discussion board to tell me about if you have tests next week, so we figure out when the actual test 2 is. And hopefully, pretty much everyone will do that today, so I can give you the test date later today. I'll send out an announcement. And the second thing, start working through this is 4.2. The next two sections are, again, doing line integrals, but for two different setups. One is, the next section is looking at what is called conservative, which we talked about in 4.1, so now we're actually using it, so we'll actually do some examples. And in that case, things will become nice. And then the section after that is saying if we have a closed path like this one, we're going to be able to rewrite this line integral like a typical double integral. So pretty much the next two sections of this one are looking at cases where we can do line integrals in a different way. So we're going to be doing line integrals for the next class or two. Definitely at least a couple of classes. So any questions on this? Okay, so usual thing, first let me ask if you have any quick questions again, and then otherwise we are done. But I'll stick around if you have more specific questions once I stop recording. So any questions? Okay, so I'm going to stop recording.